In this video, we'll discuss one-to-one and inverse functions. So the concept of one-to-one is a relation between two sets in which every element in the range has exactly one element of the domain mapping to it. We can check this by looking at the horizontal line test if we graph it. Now it's important to recognize that you can have a relation that is one-to-one and not be a function. Additionally, not all functions are one-to-one, so it's important to check relations for both of these opportunities. So let's look at a few examples. Here we have a mapping of the domain to the range, and we have elements in the domain mapping to elements in the range. And we want to know, is this a function? Well, we look at the domain. Every value in the domain is used exactly one time, therefore it is a function. When we look at the idea of one-to-one, every element in the range has exactly one mapping to it from the domain, so yes, this is a one-to-one function, or a one-to-one relation. Now, when we look at this relation, we see that we have three ordered pairs, and those are 2, 6, 3, 6, and 4, 6. Now, each value for x is being used exactly one time, so it is a function. However, when we look at this relation, we notice that this y value is being used for all three ordered pairs. So all three are mapping to the same y value, so this is not one-to-one. Now here is our third example where we have a graph, and we want to know, is this graph a function? Well, this is a parabola that opens horizontally. And to check for functionality, we look at it with the vertical line test. And when we apply the vertical line test, we see that it hits the graph at two different places everywhere on the graph except at the vertex. And because of that, we would say this is not a function. However, when we check one-to-one, we're looking at the horizontal line test. And if we take a horizontal line through this horizontal parabola, we see that it hits at exactly one place everywhere along the parabola, so it is one-to-one. So it's not a function, but it is one-to-one. Now, what does it take to make inverse functions? So it's important to recognize that an inverse function undoes the original operation of the function. When we write f of x as the function, then we write f raised to the negative 1 as the inverse. Now, the inverse will only exist when the function that we start with is one-to-one. So that's why we need to know what that one-to-one means and how to check it. When we graph the inverse, it will be the reflection of the original function along the line y equals x. So we have nice symmetry between these two functions. And if we want to check it, what we know is that the inverse of the function of fx, we know that when we do the composition of those two functions in both directions, they must equal x for it to be the inverse. So if we want to check it, we can graph it, or we can look at it algebraically. So here we have two functions, e raised to the x minus 2, and then we have g of x equals the natural log of x plus 2. And we know, is that g of x the inverse of f of x? So if we graphed it, we'd start with the e to the x minus 2. And we'd say, okay, well, when we look at that, that function is one-to-one. I can tell that graphically. Now, what does that mean for trying to understand the inverse? So let's graph g of x. When I graph it, I can say, oh, that actually does look pretty symmetric, but is it along y equals x? So let's put in y equals x here. And we say, yes, actually it is symmetric along the line y equals x. So we would say, yes, graphically, we can tell this is the inverse of e to the x minus 2. Now we can check it algebraically as well. Here we do our composition of functions. So we're going to say, what is f of g of x? So we're going to take that expression for g of x and plug it in for x in our f of x function. So that would be e raised to the natural log of x plus 2 minus 2. And we have to recognize this right here, this is a logarithmic relationship that we know that these will simplify and leave us with x plus 2 minus 2. Now we can simplify 2 minus 2 and say that f of g of x equals x. Great, that's what we wanted to do. Now let's check it the other direction though and check this composition. So we're going to take the f of x function and substitute in for all the x's in g of x. Here we get the natural log of e to the x minus 2 plus 2. Well, minus 2 plus 2 will simplify it to 0, and then I'm just left with the natural log of e to the x. Now, if you want to think about how do we do this, using logarithms, we technically are going to move the x out as the coefficient. That's following one of our log rules, and then the natural log of e is just 1. Therefore, we're left with x. Since both composition of functions equal x, we know that it is an inverse. Now, what if you want to create the inverse function? First, we need to make sure that our original function is 1 to 1. Then we swap the x and the y value, and we rewrite this new equation for y. That creates the inverse function. Now, it's important to recognize what is the domain of your inverse function. And what we know is that the domain of our inverse is always the range of the original function. So sometimes it may be easier to look at the range of the original function versus the domain of the inverse. So make sure you recognize that combination. So let's say that we know that f of x equals 2x plus 3 is 1 to 1. And we want to determine its inverse and the domain. So let's start by first replacing f of x with y. It's a little bit easier to work with. Now we can say let's swap the x and the y. So now we have x equals 2y plus 3. We're going to solve for y now. So we subtract 3 from both sides. Then we divide both terms by 2. Now, that leaves us with the inverse. And we could write that inverse as x minus 3 over 2. Or you could write it as 1/2 x minus 3/2. You can separate it into two separate fractions depending on what feels a little bit easier for you to understand. This puts it in that y equals mx plus b form of a linear equation, so that may be helpful for some. Now when we think about the domain, we want to consider the restrictions of the domain of this inverse, or think about what's the range of my original function. And here, there are no restrictions on either of these functions. There's nowhere that I get an asymptote or a whole, or where the function just cannot exist. So that means that my range is all real numbers. And if you need to write that in notation form, we say negative infinity to infinity. Let's look at one more example. Say that we have a little bit more of a complex, a rational function here, where we have x minus 3 over x plus 2. Now, we're being told this is 1 to 1. We want to know what's its domain and what's the inverse function. So we don't have to check the 1 to 1-ness. We're being told that it is. So first, again, let's replace that f of x with y. Now we're going to swap the x and the y's. This is where it looks a little bit more challenging, but we follow just our order of equations. Let's first multiply both sides by y plus 2. Now, that leaves me without a fraction, and then it's a matter of moving things around. First, let's distribute that x to y plus 2, so you get xy plus 2x equals y minus 3. And remember, we're solving for y, so we need to get all the y's to the left-hand side and move that 2x to the right-hand side. So let's subtract 2x from both sides, and then let's subtract that y from both sides. Now, when we look at this left-hand side, we're trying to solve for y, so we say, well, these both terms have y, how do we combine them? What we do is we're going to factor a y out of these two terms, and then that will leave us with this quantity of x minus 1. Now that we have this quantity, let's divide both sides by that quantity x minus 1. Now it'll leave us just with the y equals. In other words, the inverse will equal 3 minus 2x over x minus 1. Now we have to ask ourselves about the domain. And with the domain, we got to consider the restrictions either on the inverse function or on the range. Now, if we think about the range of the original, the highest power here is x over x, which means that there is a horizontal asymptote at y equals 1. Here, if we think about our domain, we look and say, well, the denominator cannot equal x minus 1 can't equal 0. So maybe that's easier for many people to understand. So we say, well, let's set that up. So that means x cannot equal 1 because 1 minus 1 would give us 0. So if we have to do that, we write the notation as the negative infinity to 1 union, so we use a union symbol, 1 to infinity.